In this video, we will explain USB Type-C port superspeed design for automotive applications, check the charging of legacy and modern smartphones via the Type-C port, show high power charging via the USB power delivery charging port, and explain how power delivery charging ports deal with high ambient temperature and cold cranking situations.
Hello everyone! In this video I will explain the USB Type-C charging port of this MediaTek car infotainment evaluation board.
The MT2712 evaluation board includes a USB Type-C port for data communication and charging mobile devices. The power solution for this port uses the Richtek RTQ2117C Type-C port controller with integrated buck converter. The RTQ2117C device consists of a USB Type-C DFP controller, a charging port controller, a USB 2.0 data switch, and a 3.5 amp buck converter. The USB Type-C bus features USB 3.1 superspeed with 2 data pairs. But because the Type-C connector is symmetrical and the plug is reversible, there are 4 data pairs connections at the connector. The RTQ2117C will detect the plug direction via the CC line and control the data switch via the polarity signal to select the correct data pair. The flexible 3.5 amp buck converter can operate from 3 to 36 volt input, has adjustable frequency with spread spectrum and high duty cycle, adjustable output current limit with cable compensation. It supports Type-C and legacy charging modes. Let's charge these 2 smartphones, an older Xiaomi Mi3 and a new iPhone XR model. The Xiaomi Mi3 uses the micro USB for charging, so I use a micro USB to Type-C cable for connecting it to the Type-C port. I also insert a voltage current monitor. You can see that this phone charges with 5.1 volt, 1.5 amp, which gives around 7.6 watts. Now let's connect the iPhone XR. It uses a Type-C to Lightning connector cable. When I connect this, it first charges with 5 volt 1 amps, and then it charges with 5.25 volt 2.5 amps for more than 13 watts of power. Let's use the RTQ2117 EVB to explain how this charging works. In all smartphone charging systems, the charger unit will tell the phone how much charging current can be provided. After this communication, the charger IC in the phone will then draw the current according to charger capability. Most legacy smartphones support the BC 1.2 standard. This standard uses the D+, D- data lines to communicate the charger unit maximum current to the phone. The RTQ2117C supports BC 1.2 SDP, DCP and CDP modes. In chargers with data, the CDP mode is normally used, which can support 5 volt 1.5 amp charging. Let's measure the V-bus, D+, D- and charging current when charging the older Xiaomi Mi3 with the RTQ2117 EVB. I will use a small interface board to measure these signals. The EVB is set in CDP mode. You can see that after switch on, there is some signal high-low communication on the D+, D- lines, after which the Xiaomi phone will increase the charging current to 1.5 amp, which meets the BC 1.2 CDP capability. Now we can do the same with the iPhone XR. As you can see in this case, there is no D+, D- high-low communication, but after a while the iPhone increases the charge current to 2.5 amps. The iPhone XR supports Type-C charging. It will sense the CC line in the Type-C cable to know how much current the charger unit can support. In Type-C only charging systems, the charging current is communicated via the CC line voltage level. The phone will have a 5.1K pull-down resistor. The charger unit will have a pull-up resistor or current source to set a certain voltage on the CC line when the phone is connected. In the RTQ2117C, the iSet pin controls the current source. iSet pin low sets 180 microamp current, which gives 0.92 volt on the CC line, which means 1.5 amp charging current. iSet pin high means 330 microamps, which sets the CC pin at 1.68 volt, which means 3 amp charging current. Let's measure the CC pin level with the iPhone XR connected to the RTQ2117 EVB. I will mount a switch to control the iSet pin. After switch on, you can see that the CC line is around 1.7 volt and the iPhone charges with 2.5 amps. When I switch the iSet pin low, the CC line voltage drops to 0.9 volts and the iPhone reduces the charging current to 1.5 amps. And when I switch back, the charge current goes back to 2.5 amps. You may have noticed that the V-bus voltage at the charger output is not constant. When the load current increases, the V-bus voltage also increases. This is the cable compensation feature, which is used to compensate for the voltage drop across the charging cable. The RTQ2117C uses an output sense resistor to sense the output current, and the compensation voltage can be adjusted by changing the impedance of the feedback network. Let me demonstrate this feature. I use a 3 amp adjustable load, which I will connect to this interface board on which I mounted a 5.1K CC line pull-down resistor. I will also measure DC voltage at the cable end, and I will measure the DC voltage at the RTQ2117C V-bus output. You can see that when I connect the cable, the voltage at both sides of the cable is the same 5 volt, because the load is very low. When I now slowly increase the load, you can see that the RTQ2117 EVB output voltage starts to rise, while the voltage at the other end of the cable stays nearly constant. At 3 amps load, the EVB output voltage is around 300 mV higher than the cable end voltage, so there is 300 mV drop across the cable. When I reduce the load current again, the EVB voltage drops, and at zero load the two voltages are equal again. Cable compensation helps to maintain stable charging voltage at the smartphone input connector. Type-C systems like the RTQ2117C deliver 5 volt 3 amp, so 15 watt max. But many modern smartphones charge at higher power. They use the USB Type-C with power delivery. These systems can provide higher output voltage. PD 2.0 has fixed output voltages 5 volt, 9 volt, 15 volt, 20 volt, and PD 3.0 has also an adjustable output voltage 3.3 up to 21 volt. Maximum current is 3 amp with standard cables and 5 amp with special E-marked cables. The communication via the CC line is now BMC digital communication. As the car battery is only 12 volt, a special buck-boost converter is needed to provide the V-bus voltage range from 5 volt up to 20 volt. Furthermore, this buck-boost converter needs to have good line regulation to deal with sudden battery fluctuations like cold crank or load dump. Here you can see the Richtek RTQ780 USB Type-C power delivery charging system. This IC consists of a USB Type-C PD port controller and a buck-boost controller that supports both PD 2.0 fixed output and PD 3.0 programmable power supply PPS. It has an onboard MCU and MTP memory and GPIOs that allow flexible programming of many functions, including standards like BC 1.2 and other legacy modes like Apple divider mode. The external 4 MOSFET power stage can be designed for output powers ranging from 27 up to 100 watts. Let's connect the iPhone XR to this RTQ780 EVB, which has been programmed to provide up to 60 watts of power. After switch on with the 12 volt input, you can see that initially the phone takes 5 volt 2.5 amps, but then it switches to 9 volt and charges up to 2 amps, so 18 watts. You can see that when I reduce the input voltage, the V-bus voltage stays constant, even down to 4.8 volt input voltage. And increasing the input voltage to 30 volts also keeps stable operation, due to the excellent voltage regulation of the RTQ780 buck boost topology. Let's measure the V-bus voltage, CC line communication and charge current. You can see there is some CC line communication when the V-bus voltage changes from 5 to 9 volts. After connecting the phone, the RTQ780 board will first tell the phone what voltages and currents it's able to deliver. We call these the source capabilities. And then the phone tells the charger which voltage and current it wants to use, based on its battery and charger system. We call this Synch capability. Then the source will apply the new voltage to the V-bus. And the Synch, the phone, will then control the battery charger and draw the current based on the power that was agreed upon. To check the data communication between the charger and the phone, let's hook up a USB PD protocol analyzer. It will translate the CC line communication between the charger and the phone. The lower window shows the bus current and voltage. It starts at 5 volt, then rises to 9 volts. In the top window we can see the communication. Here you can see the RTQ780 providing its source capabilities: 5 volt, 9 volt, 15 volt and 20 volt 3 amps, and 2 adjustable profiles. Here we see the phone first selecting the 5 volt profile, and then later on it selects the 9 volt profile. You can also see that this phone uses the PD 2.0 fixed profile specification. Here I have a Xiaomi 10T Pro smartphone. This phone uses the Type-C bus, so I use a Type-C to Type-C cable. After connecting the cable, it starts at 5 volt, then switches to 8.7 volt, which gradually increases to 9.6 volt and 2.4 amp charging current, so 23 watts of power. You can see that there is now much more data communication on the CC line. The data logging also shows this. The voltage and currents are rising gradually during charging. When we look at the data communication, we see that the RTQ780 provides its source capabilities as before. The phone first selects 5 volt, but then it selects the adjustable profile 8.84 volt 2.45 amps and gradually selects higher and higher voltages in small steps. This Xiaomi phone uses the PD 3.0 spec, which can let the RTQ780 charger operate in adjustable power supply PPS mode. Based on the voltage levels, this phone seems to be using direct charge divided by 2, where the phone includes a high-efficiency switched capacitor step-down circuit that bypasses the battery charger in high-power charging mode. 45 watt or higher power delivery chargers can also charge notebook PCs. Let's use an RTQ780 45 watt evaluation board to charge this MacBook Air. I will connect the USB PD protocol analyzer and the power monitor. After switching on the power and connecting to the notebook, you can see that the MacBook Air starts charging. The charging V-bus voltage is 20 volt and the current gradually increases. The data logger window shows at the bottom the red 20 volt V-bus voltage and the blue slowly rising charge current. Let's look at the data communication. Here you can see that the RTQ780 board is sending its source capabilities, which includes the 20 volt 2.25 amps 45 watt power profile. The MacBook Air then selects this profile. The charging power gradually increases up to 43 watts. High ambient temperature can be critical for these high-power charging systems. The RTQ780 has an A to D converter for sensing temperature via an NTC. The power delivery communication allows the charger to reduce the maximum power during charging, which can be used to reduce the power losses in the system. I have mounted a thermocouple close to the NTC on this 45 watt board. Let's check the charging and data communication when I heat up the board with hot air. Above 105 degrees Celsius, there is PD communication and the charging current suddenly reduces, then starts to rise again. In this board, the RTQ780 has been programmed to sense the NTC voltage, and at 105 degrees C, it will send new source capabilities, this time 30 watt maximum. The MacBook Air will then reduce its charging current and finally charge up to around 28 watts. This will reduce the total losses and the board temperature will drop. When I let the board cool, you can see that at 85 degrees C there is another PD communication and the charge current reduces and rises again. This is because the RTQ780 has been programmed to send the 45 watt source capability when the NTC temperature drops below 85 degrees C, and the MacBook Air will start charging at high power again. We can verify this behavior from the PD log. You can see that initially the RTQ780 provides the 20 volt 2.25 amp 45 watt maximum power profile, and the MacBook Air selects this profile. At 105 degrees C, the RTQ780 sends new source capabilities. Now the maximum power profile is 20 volt 1.5 amps, so only 30 watts. The MacBook Air then selects this lower power profile and it will increase the charge current up to 1.5 amps. When the system temperature drops below 85 degrees C, the RTQ780 sends out the full power 45 watt profile again, and the MacBook Air chooses this profile and starts charging at 45 watt power again. The RTQ780 can be programmed to adjust the charging power in such a way that the board temperatures will always stay within safe limits. Let's check how this 45 watt charging system behaves during cold cranking. I will use the cold cranking generator and the RTQ780 45 watt EVB. The cold crank output is connected to the RTQ780 EVB input, and I will measure the input current. I will also measure the USB V-bus output voltage and the RTQ780 buck boost input voltage. I will charge the MacBook Air as before. When I switch on the power, you can see the 12 volt car battery input voltage, the 20 volt V-bus voltage and the input current, which is slowly increasing as the charge current increases. At 12 volt input and 45 watt charging power, the input current is around 4 amps. When I now enable the cold crank generator, the input current will increase when the input voltage drops, since the output power stays constant. The lower the input voltage drop, the higher the input current peak. At a certain moment, you see that when the input current peak reaches 9.2 amps, the V-bus output voltage starts to drop. Let's zoom into this behavior. Initially, the input current rises when the input voltage drops, but here the input current does not rise anymore, and the buck boost output voltage will drop. In this case, the buck boost converter input current limit has been reached. For this 45 watt design, we set the RTQ780 input current limit register value to 9 amps to avoid excessive input current during low battery voltage. Charging systems like this often use a 10 amp fuse in the input rail, so the 9 amp buck boost input current limit will avoid burning the fuse during cold crank. When the V-bus voltage drops too deep, the MacBook Air will sense this and will stop charging. Then the charging system resets itself and the new charge cycle starts. This behavior keeps the charging system safe, even at high power charging and sudden battery voltage drop. I hope you now have a better understanding about electronic power design for automotive applications. Please stay tuned for more interesting videos at Richtek, your power partner.